Hello guys, today in this video we are going to discuss about non-equilibrium excess carriers in semiconductors. So as you can see in the heading itself, non-equilibrium. Non-equilibrium means non-equilibrium in semiconductor means some external excitation must have given right to the semiconductor, like in the form of some applied voltage or in the form of some energy, photon energy or something, or thermal energy, right? So anything, some external agent or external form of excitation is given to the semiconductor which is in thermal equilibrium. So for example, if you are considering a p-n junction, okay, or where we combine p type material with n type material, then in this p or n region we have concentrations of electrons and concentrations of holes, depending upon what kind of dopant atoms you have added or you have doped with, right? So if you'll see in thermal equilibrium, when the semiconductor is in thermal equilibrium, thermal agitation is still happening, right? So because of the room temperature, some electrons will gain energy and will move from the valence band to the conduction band, right? So the holes will be created and the electrons will be created in the conduction band, and these are the intrinsic carriers which will actually contribute to the process of conduction, right? So this is what we said in thermal equilibrium. So the generation of electrons and holes, okay, will be there every time, and similarly the recombination of the electrons and holes will be there. So what do you mean by generation? Generation is nothing but the process of creation of electrons and holes in the conduction band and valence band respectively, because of thermal agitation of the electrons from the valence band to the conduction band, right? Similarly, the recombination, if I'll say, what do you mean by recombination? It is the process where electrons and holes are annihilated. Okay, so destroyed, or you can say, some electrons, from the conduction band will transit to the valence band, and as a result, will be recombined with a hole. So the concentration of electron in the conduction band and the concentration of hole in the valence band will decrease. So this is what is generation and recombination. Let me just give you some visual over here. So suppose this is your conduction band, this is your valence band. At any temperature, nearly 300 Kelvin or room temperature, we said this amount, the amount of energy that is that can be taken by the electrons here in the valence band is enough, right, for these electrons to be elevated to the conduction band. So few of the electrons, as we said, intrinsic carrier concentrations. Okay, so here you can see when they, I mean, from the valence band electrons will go, you will or it will leave holes over here, and you got the electrons over here. This process is known as the generation of electrons and holes, electrons in the conduction band, holes in the valence band. Okay, at the same time, there is a possibility that the electrons which are already there in this you know conduction band will undergo collision and there will be loss of energy. So it may happen that the electron will transit from the conduction band to the valence band, right, this way. So electron will come here, right, and here there are holes already you got. So recombine these holes so that the number of electrons will be lost here and the number of holes will also be lost here in the valence band, and the process is known as the recombination. So carrier generation and recombination. So this is what we are going to understand. So now in thermal equilibrium, what we said, in thermal equilibrium, the concentration of electrons and concentration of holes in the conduction band and valence band remains the same, right? For example, you said the concentration of electron in the conduction band is n00. I'm writing for thermal equilibrium, right? Say this n0 value, and or p0 value, you said the concentration of holes in the valence band. These are all constant value, right? At a particular temperature, if you will see, the concentration of electrons and concentration of holes in thermal equilibrium is constant, right? It is independent of time, right? So there is no change in the concentration of electron or the hole with respect to time. It remains constant throughout, right, at a particular at a certain temperature. That doesn't mean that there is no generation and recombination happening. There is the process because it's a dynamic form of the, when the temperature is nearly equal to 300 Kelvin, the electrons are actually gaining energy, atoms are vibrating, electrons are gaining energy and losing energy frequently. So there will be generation and recombination processes happening, but the rate of generation, if I'll say the rate of generation, so rate of generation, when I said the number of electrons created, right, must be equal to the number of electrons annihilated. So the rate of generation must be equal to the rate of recombination. Okay, so if this is happening, then we can say recombination. Then we can say that N0 and P0, the concentration of electrons and holes, they are independent of time. Okay, so the concentration remains constant. So this is what we can say. So if I will write some notations to just denote what is rate of generation of electron. Suppose I will say Gn0. So as we said, it is, electron regeneration and hole regeneration. These are all happening in pair, right? What do you mean by this? Electron was there here in the valence band, and when it will be elevated from the conduction band to the valence band, what you got? You got the electron created over here, and similarly a hole is created here in the valence band, right? Hole is created here. So it is happening in pair. You can see one electron hole pair is created. So we can say number of electron created, or the rate of generation of electron, must be equal to the rate of generation of holes, right? It is happening in pairs. Okay, so electrons and holes are created in pairs. So we can write this to be G for generation, N for the electron generation, 0 for thermal equilibrium we are writing. Similarly, we can write GP0. So one electron created means one hole will also be created, because we said it is direct band to band generation. Direct band to band generation means what? The electron is transiting from the valence band directly to the conduction band. So this way we can write. Similarly, the rate of recombination, when we said one electron is recombined with one hole here in the valence band, then loss of one electron will create loss of one hole, right? This way. So the recombination of electron, that is loss of one electron or annihilation of one electron, is annihilation of one hole as well, right? So we can write, suppose I will write the notation for recombination of electron in thermal equilibrium, can also be written as recombination, R for recombination of hole in thermal equilibrium. This is also applicable to direct band to band recombination. Okay, so electrons and holes will also recombine in pair, right? So this is what we can say. So we can write now, in thermal equilibrium, when you said the rate of generation must be equal to rate of recombination, then we can, equate all these Gn0, that is generation of electron in thermal equilibrium, must be equal to Gp0, that is generation of hole in thermal equilibrium, must be equal to Rn0, that is recombination rate of electron in thermal equilibrium, must be equal to recombination rate of hole in thermal equilibrium. So we can equate all these, right, in thermal equilibrium when there is no other external excitation, okay, to these semiconductors. So rate of generation of electrons and holes will be rate of recombination of electron and holes if for a semiconductor. This is what we said. Okay, so once this is done, let us now see what do you mean by excess carrier generation and recombination. Excess carrier, suppose you had, like, N0 was the concentration of electrons, right, and P0 was the concentration of holes. Okay, now when you are giving us some form of external excitation, some form of external excitation means what? You can give a, like, what external excitation in terms of potential, right? External excitation in form of some photon energy incident on the semiconductor, external excitation in terms of thermal energy, so anything, right? So that, if that is given, then what will happen? the concentration of electrons and holes will be a function of time, because the till what amount you are giving that external excitation, right? So as that will vary, and what is the amount of energy that is given, right, in the form of external excitation, depending on that your concentration will also change, right? The concentration of electrons and holes will also change. So what we can say is, when high energy photons or any external excitation in the form of thermal energy or in the form of applied voltage, right, given to a semiconductor, electrons and holes are created in the conduction band and valence band. So more number of electrons and holes will be created in the conduction band and valence band. Okay, so electron and hole a pair will be generated, more electron and hole pair will be generated, right? So these additional amount of electrons and holes that were created because of this external excitation, okay, we call those as excess electrons or excess holes. Okay, so suppose I will write like n, the new value of the electron concentration can now be written as n0, which was the thermal equilibrium electron concentration, plus suppose some delta n I will write, that is the excess carrier that is created because of the excitation, external excitation in the form of applied voltage or in the form of incident photons or in the form of thermal excitation, whatever. Okay, so the same way you can write the non-equilibrium hole concentration can be written as the equilibrium hole concentration plus that extra excess holes that is created in the valence band. We can write this way, right? Now, if I'll use the notations, for example, if I'll write small g, now I'm writing capital G I had written for thermal equilibrium, small g just to differentiate it. So Gn prime. Okay, suppose I will write this is the generation rate of excess electrons. Okay, so the generation rate, these are the notations we are going to use: generation rate of excess electrons. Okay, similarly Gp prime, if you write, you can write the generation rate of excess holes. Okay, and if you want to write the unit of generation rate, means what, number of electrons or number of holes created, right, per unit volume, per unit time, right? Because rate, we said rate of generation means with respect to time you are saying, and number is always referred to per unit volume. So here if one wants to write the unit of these rate of generation or rate of recombination, you can write it actually what number, or you can say what units, what numbers, okay, were created per unit volume, centimeter cube in small dimension, as we are dealing with small dimension, centimeter per unit time second. So this way you can write. Okay, so the unit of generation rates or recombination rate can be written this way. Okay, so for a direct band to band, as I said, okay, this is your EV and this is your EC, you gave some external excitation, because of that some more pair of electron and hole were created. This gives you what, the rate of generation of electron must be equal to the rate of generation of holes over here, right? So we can write that. So if I'll write Gn dash can be written as Gp dash. So the excess number of electrons or hole pairs created will be the same. Gn dash is equal to this, right? Okay, and the second thing we said is, the non-equilibrium carrier concentration will be given by thermal equilibrium carrier concentration plus this delta n, that is the excess carrier generated because of the external excitation. The same is applicable for the holes created over here, right? So this is what we can say. N0, P0 are the thermal equilibrium concentrations here, you can see. Okay, and this delta N and delta P here are the excess electron and hole concentrations, right? So the external force disturbs the equilibrium condition in the semiconductor, okay, and the semiconductor is no longer in thermal equilibrium. So if it is not in thermal equilibrium and is in non-equilibrium condition, so what we can write is, initially in thermal equilibrium you said N0 P0 must be equal to Ni square, but now the product of N and P will not be equal to the above equation that we wrote, N0P0 is equal to Ni square, because this is applicable for equilibrium condition, thermal equilibrium condition. Now here we said it is in non-equilibrium condition because you applied a thermal excitation or external excitation in the form of photon incident or in the form of applied voltage or something like that, right? So the excess electron and holes, okay, we got, okay, that will actually violate this law of mass action, which is N0P0 is equal to Ni square in thermal equilibrium, but now it is not following the law of mass action, or N0P0 equals to Ni square. Okay. So now, so we discussed about the rate of generation of electrons and holes, which is band to band, and the rate of generation of electron will be equal to the rate of generation of hole, okay, in non-equilibrium. Similarly, the excess electron and holes will recombine in pairs, right? So the same way, like, if, because of some external excitation, if there will be recombination, then one electron will be recombined with the hole over here. So loss of electron and loss of hole you will see, right? So here also you can write, like, if I'll write R is the recombination here, if I'm writing in small, okay, and this small means that gives you non-equilibrium, you can write capital R as well, no problem. Rn prime must be equal to Rp prime. So that means what? The recombination rate of electron in non-equilibrium must be equal to recombination rate of hole in non-equilibrium. So this the same way that we discussed for the generation. Okay. So now the rate at which electrons recombine, okay, the rate at which electrons recombine must be proportional to the electron concentration and hole concentration. So the rate at which electrons recombine must be proportional to the electron concentration and hole concentration. If there are no electrons or holes, there can be no what? Recombination. So now how many electrons will be recombined with this number of holes? Okay, that purely will depend upon what is the concentration of electrons over here, and how crowded the holes are in the valence band, right? So conduction band and valence band, so depends upon the concentration of the electrons and holes, right? So the recombination rate, when I said recombination of electrons you can say, or recombination of holes you can say, right? So mathematically, if you want to write this, okay, the variation of these excess carriers, okay, then how we will write? Okay, so initially we got the change. What is the change? Initially it was N0 P0, now it became N and P. Okay, what is the difference? So we said N is equal to actually N0 plus delta N. So this term is independent of time, this is constant throughout. Now this delta n is actually what? A function of time. That's why your n will also be a function of time. This will also be a function of time, because this delta n is a function of time. Right. Now, similarly, p can be written as p0 plus delta p, we said. Now delta p is a function of time. So this p whole concentration will also be a function of time. Simple. So now we will try to write it in a mathematical form. So what I will write, what is the net rate of change? Net rate of change in the electron concentration. So what I can write for that? So I said net rate of change d by dt, to find out the rate of change of the electron concentration. So suppose, what is the excess electron concentration? We got delta nt is a function of time. We said it varies, it depends, because it's a non-equilibrium, right? So this can be written as is directly proportional to what is the difference in the law of mass action. This was our reference value, which was constant N0 P0, minus this is your NT, non-equilibrium concentration of electron, and non-equilibrium concentration of hole. We can write this. Just now we said the rate of recombination of electron, rate of recombination of electron is directly proportional, or must be proportional to what? The electron concentration and hole concentration. Now this was the standard value that we got in thermal equilibrium, which was not disturbed, which was constant throughout. Now because of this external excitation, you got a new value, so of n and p. So you can take the product, then you can find the difference between them. So that will be the measure of what? This rate of change of rate of change of, or the variation of the electron concentration, right? So this is common or a simple, argument we can take, right? So where, after this we can write, this proportionality constant can now be written like this way mathematically: d by dt of delta nt, this is the variation of the excess carriers, can be written as some proportionality constant I'm writing as alpha r. Okay, alpha r. So that proportionality constant r here is for the recombination rate. Okay, small r we are writing. Okay, just to distinguish it, okay, or differentiate it. Ni square for n0 p0 minus this nt pt we have, right? And these values of nt and pt I have already shown. You can again see this, what is nt and what is pt. So the excess carriers plus the thermal equilibrium concentration. Similarly, pt we can write this as p0, thermal equilibrium whole concentration, plus the excess carriers. Okay, the excess carriers here you can see are the function of time here in non-equilibrium, so that the total concentration will also become function of time. Okay, so now let us take the excess electrons and holes. They are created in pairs, we said. So the rate of generation and rate of recombination both happens in pair, right? So here we can write the number of excess carriers, okay, excess carrier electron is equal to the number of excess carrier hole created, because they all occurred in pair in band to band generation. So considering that this excitation is also from direct band to band, we can take that delta n is equal to delta p, right? So here if I'll just substitute it, what we can take is delta nt is equal to delta pt, as they created in pairs. Okay, so this way, or we can take it's a direct band to band generation, right? So let us substitute it, then rewrite it: d by dt of delta nt. In our previous equation, alpha was the proportionality constant, ni square, minus your n value I will substitute that n0 plus delta n. Okay, delta nt is there, I'm just writing it as delta n just to make it look simple. P0 plus delta p is a function of time again. Delta n and delta p are function of time. Okay, so that we can write alpha r here ni square minus n0 p0, open the bracket, and then n0, and you have delta p, delta p function of t actually this is. So p0 delta n minus delta n and delta p. Okay, this is both are function of time. Delta n and delta p are always function of time. Okay, this we got, right? Now we can rewrite is d by dt of the whole thing, delta n function of time, okay, must be equal to minus alpha r. We have n0 plus p0 plus delta n, which is function of time, and this is delta n taking out. Okay, because we have delta n is equal to delta p, you substitute delta p as delta n here, delta p as delta n here, and take this delta n out, right? So this is what we got in this, right? D by dt of delta nt is equal to minus alpha r n0 plus p0 plus delta n function of t whole into delta n plus. Okay, so now if we will consider the p type semiconductor, okay, if we'll consider for a p type semiconductor and low level injection. So let me just tell you what do you mean by low level injection. Low level injection means, okay, thermal excitation we did, right? So when we are talking about thermal excitation or external excitation, sorry, not necessarily thermal excitation, any other form of external excitation you can consider, like we said photon, incident photon, or applied voltage, or thermal agitation. Okay, so whatever. Now, here for P type, if I'm writing for P type, we have P0, so thermal equilibrium hole concentration is much larger than N0, right? Okay, and when there will be injection of, for example, electrons will be injected, right? To this, electrons will be injected, more electrons will be injected because of the thermal excitation, right? So that will create extra or excess carrier electrons here, right? Excess carrier electrons here. Then here for low level injection, we have the boundary condition that the original, concentration of holes over here, is much larger than whatever the, excess electrons are injected, okay, because of the thermal excitation. So that is what we will call as low level injection. So low level injection. So normally this terminology is used in all of the textbooks and all. So if you'll see low level injection, what does it mean? It means that whatever excess carriers, okay, are entering or were injected in this p region, okay, if you will consider the concentration of these excess carriers, which is, we said, delta n, okay, this is actually much less than what the original thermal equilibrium concentration of holes, then we will refer it as low level injection. Okay, so high level injection will be just opposite, when this delta n or the injected magnetic carriers are much larger than what the original thermal equilibrium concentration, that will be considered as high level injection. Okay, so anyways, so here we are considering p type under low level injection. So here we are considering this low level injection. Okay, so for this, what we can write, as we said, p type, definitely p0 is much larger than n0, p type. And the second thing, we said low level injection, so I can write p0 is much larger than this delta nt, function of time, so excess carrier concentration. So we will use this, okay, to rewrite the previous equation. What was the previous equation? The previous equation was this: d by dt of delta nt is equal to minus alpha r multiplied with n0 p plus p0 plus delta n, right? Now what we considered here, we considered that the p0 value here is much larger than n0, okay, and also p0 is much larger than delta n. Okay, so this is for a specific condition. What is the condition? P type and low level injection. So p type and low level. So p type, for p type, what we said, sorry, for p type we said p0 is much larger than n0, and low level injection, what we said, p0 is much larger than delta n. So now if I will ignore this n0 and delta n, okay, as comparison to p0, I can only write p0 value here in this equation. So the whole equation can be written for this specific condition, that is p type and low level injection. You can write d by dt of delta nt must be equal to minus alpha r, and here this p0 term, and then delta n. Okay, so I will write for this particular condition, p type under low level injection, we can write the variation of the excess carrier concentration, which is delta nt, for p type under low level, can be written as minus alpha r p0, and this is delta nt, right? So you can see this is in the form of dx by dt is equal to some constant over here, okay, minus this constant and x, right? So this is in the form. So the solution to this equation can be written as exponential decay. As you can see, dx by dt is equal to minus some constant k and x, right, minus kx, in that form. So here the solution, if you write solution of this differential equation, can be written in this form: delta nt, okay, so excess carrier concentration as a function of time at any time t can be written as some initial concentration delta n0, where t is equal to 0, you said, that's the initial concentration, e to the power minus alpha r p0, that constant, and then you have this t, right? So the solution of this differential equation can be written this way, right? So it's an exponential decay function. If you can see, delta n gives you the excess carrier concentration at any time t, can be written as delta n0, some initial concentration here, multiplied with e to the power minus alpha r p0, proportionality constant, and p0 is also constant, thermal equilibrium hole concentration, multiplied with time. So as the time increases, you can see that the excess carrier will fall exponentially. So there will be exponential decay from some initial concentration delta n0, right? So further, if you want to simplify it, delta nt can be written, can be written as delta n0, and then e to the power, I will write it as minus t by tau n0, just to simplify it further. Tau n0 here we wrote, okay, where I just substituted tau n0 for, actually this is 1 by alpha r p0, or let me just write alpha r p0 inverse. Okay, this way we can write. Okay, so this particular equation is now, if you will see, okay, represents an exponential decay, right? So this actually gives you what, the decay of excess minority carrier electrons. This equation describes the decay of excess minority carrier electrons. Excess means what? Because of the non-equilibrium, or the in the form of external excitation, you created this excess amount of electrons in the p region, right? So this excess carriers will actually decay with time. You can see the time factor here, okay, and some initial concentration, okay. Then it will decay exponentially, okay, exponentially it will decay. So this is the, this is the equation that we got. And what is this tau n0, which we wrote as alpha r p0 minus 1? Okay, we can say this is actually what, the excess minority carrier lifetime. We can write this way. Okay, so what is this? Excess minority carrier lifetime. Carrier lifetime. Okay, so this way we can write. Now what is the recombination rate of excess minority carrier electrons? Okay, recombination rate of excess minority carrier electrons, okay, which we got. So d by dt of delta nt, which we wrote in this form, like, delta n0 e to the power minus t by tau n0, right? So this is the rate of excess, minority carrier electrons, recombination rate. So now we can further write it as, like, if I'll write R n prime, which we started with, recombination rate of the excess minority carrier electrons, can be written as rate of decay, as we said. Okay, recombination, that means the concentration will decrease. So I'll put a minus sign, and then I will write d by dt of this delta nt factor, okay, okay, which can be written as alpha r p0 delta nt. Okay, just revisit to this equation where we wrote, we considered n0 and delta n to be very very less than p0. We got alpha minus alpha r, then p0 delta n. Now I put minus, one more minus sign, saying that recombination is the decay of electrons and holes. So decay of electrons over here. So we wrote minus minus plus, so alpha r p0 delta n. That is what I'm going to write here. So minus, and so minus minus became plus, alpha r p0 delta nt, right? So which is your, actually what, delta nt divided by tau n0, delta nt divided by tau n0, because we substituted this alpha r p0. What we wrote for alpha tau n0? Tau n0 is, actually we considered alpha r p0 inverse, right? So simply we can write this way. So what we got, r n prime, the recombination rate of these excess electrons, excess minority carrier electrons in p region, can be given by this. Okay, so what is this negative sign? As I told you, the negative sign that we put over here, as the minority concentration decreases with respect to time, right? Because it's a recombination. Okay, so for direct band to band recombination, the excess majority carrier holes, okay, excess majority carrier holes recombine at the same rate. So if you want to write it, like, as we said, Rn dash is equal to Rp dash. So the same way we can write for the P region we are writing. So it can be written as delta Nt divided by tau N0. So Rn dash is equal to Rp dash, because we considered band to band recombination, right? So similarly for N type, if you want to rewrite it, so this is for P type we said. So for P type, you can see for P type, this Rn is considered to be the recombination of N is what? The minority charge carrier in P region. So excess minority carrier concentration we said, and R is recombination rate in non-equilibrium. P is what? P is considered to be the majority charge carrier in P type in the P region. So we said the excess majority carrier holes, P is for holes, okay, recombine at the same rate, and we got this. So this is done for P type. Okay. Similarly, you can do it for N type. Okay. So N type, what you will write? For N type, if somebody will write for N type, okay, for the N region, similarly N0 is much larger than P0. This is first thing, right? And then for low level injection, like we did it for P type, low level injection, we can say that this majority charge carrier N0 is much larger than this excess carrier concentration delta NT, right? This way you can write. And here when I'm writing delta NT or delta PT, don't be confused, because we said delta NT is equal to delta PT. So either you write delta NT or delta PT for a band to band generation or recombination. We got this excess carrier concentration will be the same, right? Delta NT is equal to delta PT for band to band, direct band to band regeneration and recombination, okay, generation and recombination. So here the same way we can write, substituting all these and writing for tau p0 the same way, alpha r n0 minus 1, okay, the same way like we did here. So here we wrote tau n0 is equal to alpha r p0 minus 1. You can write tau p0 is equal to alpha r n0 to the power minus 1, right? So that is your excess minority carrier lifetime. The same thing I'm writing, lifetime. Okay, so you can write the recombination here. Okay, like your Rn dash is equal to Rp dash for the N type you are doing. For the N type can be written as delta Nt divided by tau P0. So this is for N type, and for P type we wrote for P type, rewriting it again. So Rn dash is equal to Rp dash, gives you delta n t divided by tau n0. So what is important, you need to see that what is that minority carrier lifetime of the electron, okay, in the P region, and what is the excess minority carrier lifetime of holes in the P region, okay, in the N region, sorry, in the N region. So here you can see this tau p0 for the N region and tau n0 for the P region. So that will decide actually how, I mean, how much time it will take to decay completely to what? The thermal equilibrium concentration. So till I mean, what time it will exist, and up to what time it will come back to the thermal equilibrium concentration. So who will decide this? Who will decide this? The value here, actually we said that is delta nt is equal to delta n0 and e to the power minus t by tau n0. So you can say this is the exponential term which will actually decide the decay, right? So at what time actually it will decay completely, the excess carriers that were created. So that when you are writing n is equal to n0 plus delta n, with time this delta n factor will decay and will become n0. So when this delta n will be 0, this n will be n0. Same will happen with p. P is equal to p0 plus delta p. So this delta p will exponentially decay with time, which depends upon the excess minority carrier lifetime, and will be 0 here. Then your p non-equilibrium hole concentration will be thermal equilibrium hole concentration. So this is it for this video. We will continue with some other topic in the next video. Thank you for watching. Stay tuned.